Hello everyone, my name's James Hazard and I'm a PhD student at Imperial College London. My talk will focus on my work to reduce uncertainty in upper mantle rheology and rates of glacial isostatic adjustment using a Bayesian inverse framework to calibrate experimental parameterisations of anelasticity. This framework has been developed to be applicable anywhere in the world, but I will focus on my work to implement it to determine Antarctic structure in this presentation. My key takeaways are the development of a statistical framework for self-consistent mapping of tomographic data into upper mantle structure, as well as the use of this framework to produce high-resolution 3D models of Antarctic viscosity, lithosphere-asthenosphere boundary depth, and geothermal heat flow with quantified uncertainty. Understanding the upper mantle thermomechanical structure in the region of Antarctica is vital for the geodynamics and paleoclimate communities. However, two key issues have historically limited our ability to map this structure with confidence. Firstly, a lack of seismic stations within latitudinal proximity of the Antarctic continent has meant that the upper mantle beneath Antarctica and surrounding oceans were among the poorest resolved sections of the Earth's interior. This has recently been addressed by the ANT20 model of Lloyd et al. In 2020. Using data collected from around 300 seismic stations over the preceding 15 years, ANT20 is a tomography model offering regional scale resolution south of 60 degrees south. The model offers good data coverage across the continent and in the nearby oceans. See the paper for more details. The shear wave velocity at 150 km depth, shown on this slide, displays evidence of significant lateral heterogeneity over short wavelengths, such as a slow wave speed anomaly located beneath eastern Mary Birdland, consistent with the presence of several volcanic systems. Secondly, simple scaling relationships have been used to convert seismic data into thermodynamic parameters such as temperature and viscosity. These often fail to account for anelasticity. Our ability to reconcile modelling issues with the conversion of seismic data into upper mantle structure has been revolutionized by the development of experimental parameterisations of anelasticity, such as that of Yamauchi and Take in 2016. By using the full physics relating the strain response of the mantle to a seismic propagation, these models allow us to capture the full range of behavior affecting shear wave velocity. The importance of parameterizing anelasticity can be seen here in a plot of shear wave velocity on the vertical axis against temperature on the horizontal axis. At temperatures approaching the solidus, anelastic effects become particularly important, causing a considerable reduction in velocity associated with the activation of a process known as diffusion-accommodated grain boundary sliding. This dramatically reduces the temperatures inferred from a slow velocity anomaly as compared to previous models which assumed an elastic approximation. In the parameterization of Yamauchi and Take, shear wave velocity is a function of the mantle's density and a parameter called the storage compliance. Attenuation is the ratio of a parameter called the loss compliance to the storage compliance. These two parameters make up the complex compliance, which is a description of the frequency-dependent stress-strain response of a material. It essentially describes how squishy the material is, and can be measured in the lab using a forced oscillation setup, as shown on the right-hand side. The complex compliance is a function of temperature, pressure, seismic frequency, and a set of anelasticity parameters in the Yamauchi and Take parameterization. The anelasticity parameters are sevenfold: the shear modulus at reference temperature and pressure, and its temperature and pressure derivatives, a reference viscosity, activation energy and volume, and the depth dependence of the solidus temperature. Knowledge of the anelasticity parameters allows us to map in a forward sense between seismic shear wave velocity and interesting thermomechanical properties, including temperature and viscosity. However, there is significant uncertainty on laboratory estimates of the anelasticity parameters. Here you can see two predictions for Antarctic viscosity from the same tomography, where I've chosen two plausible anelasticity models based on laboratory estimates of each parameter. The key thing to notice here is that the viscosity output between models differs by multiple orders of magnitude. In addition, the lack of calibration against regional data means that a forward approach fails to reconcile differences in structure that arise purely from subjective choices made in the tomographic modeling process, such as regularization. The two figures at the bottom of your screen show the viscosity output given the same anelasticity model but two separate tomography models. Again, we see large discrepancies. If we instead presume that the anelasticity parameters are an unknown, We can turn this into an inverse problem and solve for the parameters by calibrating the mapping against well-constrained mantle properties. The main constraint we use is an oceanic plate cooling temperature model. In addition, we use an adiabatic temperature model, an attenuation model, and a viscosity model. To construct a plate cooling model for Antarctica, we make use of regional water-loaded, sediment-corrected basement depth age data, shown in panel A, and heat flow age data, shown in panel B. We find an optimal solution with a mantle potential temperature of 1420 plus or minus 50 degrees centigrade. By binning the shear wave velocities in our seismic model by oceanic age and depth, shown in panel A, we can construct a mapping between shear wave velocity and temperature, which is shown in panel B. We use three 25 km depth bins over the ranges 50 to 75 km in blue, 75 to 100 km in purple, and 100 to 125 km in red to characterize the VST relationship at shallow depths. To assess the misfit between data and model for this constraint, the VS measurements shown in panel A will be compared to VS inferred by mapping plate cooling temperatures into velocities given a chosen anelasticity model. As an additional constraint, a 1420 degree isentrope with temperature gradient of 0.44 degrees per kilometer will be used to estimate temperatures and hence infer VS between 225 and 400 km depth, shown in panel B. Attenuation measurements taken from the radial attenuation model of Dalton et al. In 2008 are shown in panel C. These will be compared to attenuation inferred from VS. A bulk shear viscosity constraint shown in panel D will be compared to the depth average viscosity inferred from VS. In designing an inverse framework to model this problem, we wanted to capture prior knowledge from the literature about the anelasticity parameters. Since we wish to produce 3D self-consistent maps of Antarctic structure with properly quantified uncertainty, we needed a framework that allows us to naturally propagate uncertainty in the anelasticity model into uncertainty in the model outputs. This uncertainty should take into account the covariance structure in the model space. This meant that a Bayesian approach was the most logical way to tackle the problem. A set of Gaussian priors were estimated conservatively using a combination of a literature search and statistical modeling, and they are displayed here. Once a suitable set of priors was chosen, a particular type of MCMC algorithm was used to run the inversion. The Gazwan procedure has been used elsewhere in the scientific community and is particularly useful in cases where the parameter space is multidimensional and contains significantly non-diagonal covariance. This enables efficient sampling where it would otherwise be impossible to achieve convergence onto the underlying distribution. Each sample from the inversion is a unique combination of the anelasticity parameters, making up a unique model. The result of the inversion is a set of 200,000 posterior anelasticity models. To assess the off-diagonal covariance structure of the parameter space, we can plot the sampling density of each combination of parameters, shown here. A greater sampling density indicates a more probable model. There is evidence of significant off-diagonal covariance in the parameter space, for example, between the parameters that regulate the elastic component of the response. There is a very strong trade-off between the reference shear modulus and its temperature gradient. A similar structure is seen between the parameters regulating the anelastic component of the response. For example, a very strong trade-off between the activation energy and reference viscosity indicates that a whole family of models lying along this trade-off are equally probable. To utilize the posterior samples we have generated, we first randomly select 1,000 of these anelasticity models, which are sufficient to characterize the overall distribution. As mentioned earlier, each model is a unique combination of the anelasticity parameters. By comparing our sample posterior models to the data, we can confirm that the algorithm has proceeded as expected. Here you can see the 4 mantle constraints used in the inversion, and now with the posterior model predictions overlain. Each of the posterior samples is then used to propagate VS into temperature and viscosity. We can use means and variances to investigate the size and range of the calculated structures. The first of these outputs is the mean and standard deviation viscosity structure, shown here at 150 km depth. Outside of high viscosity regions, which will be interpreted as elastic lithosphere by GIA models, uncertainty is approximately an order of magnitude less than predictions generated from forward modeling. This can be explained by 1. Our use of data to calibrate the models, and 2. Our natural treatment of the model covariance structure in the Bayesian inverse framework. Looking at the Amundsen sea embayment, we can see that viscosities are low in this region. However, our calculated value of 10 to the 19.6 plus or minus 0.3 Pascal seconds is an order of magnitude larger than that predicted by Barletta et al. From GPS measurements. This discrepancy may partially reflect the transient nature of the satellite measured value compared to our steady-state prediction. However, if physical, this would suggest bedrock topography may respond less quickly to ice mass loss, indicating a less stable West Antarctic ice sheet. The sharp viscosity boundary between east and west follows the transantarctic mountain range and is indicative of the dichotomy between old cratonic lithosphere in the east and the West Antarctic rift system. A large low viscosity anomaly can be seen extending from the Balleny Islands through to the western side of the Ross embayment. This is consistent with the presence of an active spreading centre at the Macquarie Triple Junction, as well as the recent extensional tectonics along the western margin between the Ross embayment and the transantarctic mountains. The second output of interest here is the laterally varying depth to the 1200 degrees centigrade isotherm, which serves as a proxy for lithosphere-asthenosphere boundary depth. In panel A you can see mean and panel B uncertainty. Thinner than average lithosphere predicted over West Antarctica suggests faster GIA response times when compared to 1D average LAB models. Finally, this method has been utilized to estimate geothermal heat flow by empirically fitting the calculated temperature depth structure according to the procedure set out by Mackenzie et al. In 2005. We find significantly larger heat flows of around 70 to 100 milliwatts per square meter into the base of the West Antarctic ice sheet as compared to values of 50 to 60 milliwatts per square meter in the east, except for a local heat flow anomaly in the region of the Gamburtsev Mountains. Over long wavelengths, our results are comparable to the work of Shen et al. In 2020, who compared seismologically derived Antarctic temperature structure to known heat flow in the continental United States. To summarize, we have developed a new statistical framework to self-consistently map tomographic data into high-resolution 3D models of Antarctic viscosity, LAB depth, and geothermal heat flow. These come with quantified uncertainty and are suitable for a range of potential applications. For example, our viscosity and LAB depth can be applied to 3D glacial isostatic adjustment models, where uplift rates are intimately tied to rheological structure. Our high-resolution maps of geothermal heat flow can be used to feed into new ice sheet modelling studies. These inputs should therefore help to improve both accuracy and uncertainty quantification in projections of future sea level rise.